Good evening. By now, you will have heard the wonderful news that astronomers working at the European Southern Observatory during the first half of 2016 have discovered an Earth-like planet in orbit around our nearest star. Alpha Centauri is the brightest star in the constellation of the Centaur and is only visible in the southern hemisphere. It is a triple star system 4.37 light years away from us, which is really close on the cosmic distance scale. The speed of light is 186,000 miles a second, so Alpha Centauri is only 24 million miles away. Proxima is one of its companions. It shines at the 11th magnitude and is a red dwarf star about 1/7 the size of our Sun. It orbits around its primary star at a distance of 1,400 million miles in a period of about 500,000 years. The new planet, named Proxima b, is believed to be about 10,300 miles in diameter, which is not much bigger than the Earth, and it orbits around Proxima Centauri in just over 11 days. The mean distance is under 4,700,000 miles, which places the star in the lukewarm temperature region known as the Goldilocks zone. Because its Sun is a red dwarf star, the planet is constantly bathed in red light, so astronomers are calling it the pale red dot, referring to Carl Sagan's reference to our Earth, seen from space, as the pale blue dot. Is there life on Proxima b? Well, we just don't know. Proxima Centauri is an unstable star, which is occasionally subject to X-ray flares that are harmful to life as we know it. However, it is possible that the planet has a molten core and is capable of creating a magnetic field similar to the Earth's Van Allen belts that would protect the planet and any life there from the harmful X-ray radiation, so we can't rule out completely that there is life on the planet. Nevertheless, the planet is a great discovery. Much closer to home in our own solar system is the asteroid belt, which lies between the orbits of Mars and Jupiter. It was once thought that it was the remains of a planet that had broken apart, leaving a debris trail around its orbital path. Today, we know far more about the asteroids, and astronomers believe that not only do they hold the key to the origin of our solar system, but also to life on Earth itself. In a few days' time, the NASA spacecraft OSIRIS REx will be launched into space on top of an Atlas V rocket from Cape Canaveral. It is setting out on a 2-year journey to the Near Earth Asteroid Bennu. Osiris is an ancient Egyptian god of the underworld. It represents the Lord of the Dead. He was classically depicted as a green-skinned man with a pharaoh's beard, partially mummy-wrapped at the legs, and wearing a crown with 2 large ostrich feathers on either side, while the word Rex in Latin means king. His name was chosen for this mission as the asteroid Bennu is threatening Earth and quite capable of causing destruction in about 170 years from now. The Atlas V rocket will launch OSIRIS REx. Then, with a velocity over 12,000 miles an hour. Once in space, OSIRIS will perform a series of deep space maneuvers, changing velocity by another 1,160 miles per hour, and it will then orbit around the Sun. After a year, OSIRIS will make a flyby of the Earth. The Earth's gravitational field will then pull the spacecraft towards the planet and give it a push back into space for a meeting with Bennu. The approach phase begins when Bennu is just a point of light more than 1 million miles away from the spacecraft in August 2018. As OSIRIS REx approaches the asteroid, it will use an array of small rocket thrusters to match the velocity of Bennu in its orbit around the Sun. Bennu travels around the Sun at an average speed of 63,000 miles an hour. To reach Bennu, OSIRIS will perform a series of braking maneuvers, slowing down by about 1,200 miles per hour, resulting in a relative approach velocity of half a mile a second. Asteroids can be found everywhere in our solar system. They originate from the time that the Sun and planets formed 4.5 billion years ago out of a rotating cloud of dust and rocky debris. Astronomers call this the proto-planetary disk. In the middle, the concentration built up tightly, and after a time, the temperature became great enough for fusion to begin, and our Sun lit up for the first time. The solar wind then blew away the remainder of the dust to the outer edge of our solar system. What remained formed the planets, and the leftover chunks are today known as the asteroids. Planetary scientists send spacecraft to the asteroids to study them in detail and to take many photographs of their cratered surfaces to build up a better understanding of how our solar system formed. Our solar system is made up of the Sun in the centre, and then comes the 4 terrestrial planets: Mercury, Venus, Earth and Mars. Then there is a wide gap, followed by the giant gas planets: Jupiter, Saturn, Uranus and Neptune. Pluto is today classed as a dwarf planet and lies at the outer edge of the solar system, 3,666 million miles from the Sun. The distance of each planet from the Sun can be measured in miles or kilometers, so that Mercury is 36 million miles, Venus 67, the Earth 93, and Jupiter 483 million miles, and so forth. This is a nice arrangement, however, working in miles is clumsy. Astronomers therefore use a different measure, which is based on the mean distance of the Earth from the Sun of 93.5 million miles. Astronomers call this the astronomical unit. On this scale, Mercury is 0.39 AUs from the Sun, the Earth is 1, Mars 1.52, Jupiter 5.2, and Neptune is 30 astronomical units from the Sun. So you get a sense of scale for the size of the solar system. To the early astronomers, the gap between the orbits of Mars and Jupiter was a problem. It was 3.6 astronomical units wide, which did not fit in with the distances between the other terrestrial planets. The German astronomer Johannes Kepler went so far as to write, "Between Mars and Jupiter I put a planet." However, the problem went unsolved until 1772. Then the German astronomer John Bode came across an odd numerical relationship by another German named Jöns Titius and popularized it. Today it is referred to as Bode's law. Take the numbers 0, 3, 6, 12, 24, 48, 96 and 192, each of which after 3 is double its predecessor. Now add 4 to each, giving 4, 7, 10, 16, 28, 100 and 196. If we take the Earth's distance from the Sun as 10, this series of numbers gives the distances of the remaining planets to the scale of the astronomical unit with reasonable accuracy. In this sequence of numbers, 2.8 lies in the location of the wide gap between the planets Mars and Jupiter. There should be a planet there, and it seemed to be missing. In 1800, 6 astronomers gathered in the little German town of Lilly-Lenfeld, where John Scroter had his observatory, and they called themselves the Celestial Police. Before they could begin their search, the Italian astronomer Giuseppe Pazzi, a Catholic priest who was in charge of the Sicilian Observatory in Palermo, discovered a star-like object that behaved like a planet on the 1st of January 1801. When its orbit had been worked out, it was found to have a distance of 2.77 on the Bode scale. Pazzi named it Ceres in honor of the patron goddess of Sicily. Ceres was found to be about 500 miles in diameter, lying at a mean distance of 257 million miles from the Sun, with an orbital period of 4.6 years. Ceres was indeed a minor planet, yet it was much too small to be the missing planet Bode had predicted, and so the search continued. Heinrich Olbers discovered another minor planet in 1802, which he named Pallas. Juno was discovered by Carl Harding in 1804, and Vesta was discovered by Olbers in 1807. Pretty soon, a whole host of minor planets had been discovered, and today we know of over 4,000 members lying in the gap we now call the asteroid belt between the orbits of Mars and Jupiter. The asteroids are affected by the gravitational pull of Jupiter that shepherds the small asteroids into distinct debris rings with gaps in between them. Astronomers refer to these as the Kirkwood gaps, after the American astronomer Daniel Kirkwood, who correctly explained them in 1866. There are distinct families of asteroids, and about 1/3 of the main belt asteroids belong to families named after the member with the lowest number. They are called Hirama families because they were first noted by the Japanese astronomer Kayazetsu Hirama in 1918. For example, the Flora family has more than 800 members. Coronis is one of the most populated families, with over 300 members at distances between 2.8 and 2.95 astronomical units from the Sun. Members include 158 Coronis, which has a diameter of 22 miles, and 167 Urda, which is 25 miles. We see the same shepherding effect looking at the lovely rings of Saturn. The planet has 62 moons, and they gravitationally influence the particles of ice and dust in the rings, causing the gaps. The most famous of these is the Cassini division, which is visible in small telescopes. You can see it nicely in this recent photo of Saturn taken by award-winning photographer Damian. In other areas of the solar system, we find different classes of asteroids depending on their orbits. The volcanoids lie in a stable path 13 million miles out from the Sun, well within the orbit of Mercury. The Apoheli class have orbits inside that of the Earth. Then we come to the Near Earth objects that make close passes to the Earth, and Bennu is one of these members. There are other classes of asteroids with orbits further out than Mars, and even associated with the gas giant planets of the solar system. In celestial mechanics, Lagrange points mark positions where the combined gravitational pull of the two objects that provides precisely the centripetal force required to orbit with them. The Earth has 5 moonlit asteroids, and the latest member, 2016 HO3, was discovered recently in April 2016. They all have orbital periods of about 1 Earth year, and they have distances ranging between 83 million miles at perihelion to 102 million miles. They are naturally very faint objects. Asteroid 2016 HO3 was discovered on the 27th of April by a team of astronomers led by B. Gibson, observing with the 1.8 meter Richley Creation Telescope of the Pan-STARRS project at Halilika on the island of Hawaii. It has an apparent magnitude of over 21, and its size is believed to be about 700 meters. Venus has one Trojan asteroid, which was discovered in 2013. Mars has 7, Uranus and Neptune 18, and Jupiter is known to have more than 6,000 of them. Jupiter's gravitational field is the most powerful in the solar system and captures asteroids and comets when they pass too close to the planet, some of which have been known to fall into Jupiter itself. The NASA mission to the asteroid Bennu is called Origins, Spectral Interpretation, Resource Identification, Security Regolith Explorer, or OSIRIS REx. It will be the first American mission to return samples from an asteroid back to Earth. After travelling for more than 3 years, OSIRIS will approach the primitive asteroid Bennu in 2018. Bennu is about 500 meters in diameter, and earlier this year NASA calculated that Bennu might hit the Earth on the 24th of September 2186. If this were to happen, it would be devastating. However, according to NASA, there is a 1 in a million chance that Bennu will miss the Earth entirely on this occasion. Bennu's size, ancient composition, and its hazardous orbit make it one of the most fascinating and accessible near-Earth objects, so it is the ideal asteroid for NASA's OSIRIS spacecraft to visit. Fully fueled, the OSIRIS spacecraft weighs 2,110 kilograms. It is essentially a box measuring 2.4 by 2.4 meters with a height of over 10 meters. And with the solar panels deployed, OSIRIS is 6.3 meters long. 2 solar panels, totaling over 8 square meters, will generate up to 3,000 watts of power, depending on the spacecraft's distance from the Sun. Once within 3 miles of the asteroid, the spacecraft will begin 6 months of comprehensive surface mapping. OSIRIS carries 5 science instruments and a robotic arm to gather a surface sample from the asteroid.
NASA's OSIRIS REx spacecraft is equipped with a suite of instruments designed to study its target, a Near Earth asteroid called Bennu. One such instrument is called REXIS, the Regolith X-ray Imaging Spectrometer. That complex name matches its complex task.
REXIS is something completely different than the rest of the instruments aboard OSIRIS REx. And that's because REXIS will detect elements, the individual atomic elements that make up this asteroid. Everything else is mapping the geology or the interior or even the mineral structure. And we are at the most fundamental level looking at what this asteroid is made out of.
REXIS works off of how the sun's X-ray light interacts with the surface material covering Bennu. Atoms on the asteroid absorb these X-rays, causing their electron levels to temporarily change and emit their own X-rays. These re-emitted X-rays have a specific energy that tells us about the atom that they came from. This process is called fluorescence, but you can think of it like a glow. REXIS is a telescope that images that X-ray glow, which allows scientists to create a map of the different elements present on Bennu's surface. And REXIS has the ability to do all this based on its design and its position on the spacecraft.
REXIS is about the size of a shoebox. It's located on the main instrument deck of the OSIRIS REx spacecraft. Basically, this is the side that's always facing the asteroid.
The pieces of the Rexus instrument are composed of two primary parts. We have the main Rexus telescope, which views the asteroid Bennu. It's consisting of 4 CCDs that look through a coated aperture mask. The coated aperture mask is just a stainless steel plate with a number of holes that are known to us. The second part of the X-ray instrument is called the Solar X-ray Monitor, or the SXM. The SXM is viewing the sun at all times so that we can monitor the X-ray spectrum, the solar X-ray spectrum, incident on the surface of the asteroid.
The Solar X-ray Monitor lets us calibrate out the day-to-day, even the hour-to-hour variations in the X-ray flux that comes from the sun.
So like your digital camera or camera phone, the main spectrometer uses a light sensor, known as a CCD, or charge-coupled device. In this case, there are 4 of them, and they're only sensitive to X-ray light. Before the X-ray photons from Bennu are detected by the CCDs, however, they pass through a mask with a random pattern of open and closed holes. By analyzing how the shadow of the mask pattern is shifted on the CCDs, scientists can determine the location of the X-rays coming from the asteroid's surface. This is how Rexus images Bennu. And one surprising aspect of the Rexus instrument is the team that built it, students from MIT and Harvard.
The students are fantastic to work with. They're so eager to learn. It's been great sort of watching them as they grow in this experience. And I think they've come with some interesting ideas and some ways of looking at it that we may not have had had we been someone who's been doing this for years and years and years.
Other missions have had X-ray spectrometers on board, but not nearly the level of sensitivity and sophistication of Rexus. This really is a new generation, a next generation in X-ray imaging for planetary science, and it's all being done by students.
My name is Tim Haltigan from the Canadian Space Agency, and I'm the Canadian Mission Manager on OSIRIS REx. I'm responsible for the overall operations of the OLA instrument and also responsible for coordinating the contributions of the Canadian science team. So OSIRIS REx is an international collaboration led by NASA that is a mission to go to an asteroid named Bennu, capture a sample of it, and bring it back to Earth so we can understand a little bit more what it's made of. Understanding the shape of asteroid Bennu is going to be absolutely fundamental to understanding the geology and putting it in context. The other reason you really need to understand the topography extremely well is that when we're going in to take a sample, it's a very, very fine measurement. And so if you're coming in, you've got the sampling head at the end of this arm that has to come in perfectly square to the surface. If you don't understand shape, sort of at a 30 centimeter scale, you're not going to be able to collect a sample. So OLA, or the OSIRIS REx laser altimeter, is an instrument on the spacecraft that has 2 lasers inside of it, and it acts sort of like a 3D scanner. OLA is going to create a 3-dimensional map of the entire asteroid Bennu at a resolution of about 1 point every 7 centimeters. This operates very similar to a radar. However, instead of using a radio wave, it uses light. And so by measuring very accurately how long it takes for that laser pulse to go out and bounce off a surface and come back, you can measure a very accurate distance away from the spacecraft. The reason we have 2 different lasers is that we have to measure the asteroid from different distances away from it. So the high-powered laser we can use from about 7 kilometers into about 1 kilometer away from the asteroid. The low-energy laser we can then use from 1 kilometer and inwards. And so as we get closer and closer to the asteroid, we can make a lot higher resolution maps and understand the shape of certain regions even better. The Canadian Space Agency contributed OLA to this mission for a number of reasons. First is that it allows Canadian scientists to have access to astromaterials for the very first time. So these are the first samples that are coming back on a sample return mission that Canada is going to own a portion of. The second reason is that it really highlights the expertise of Canadian scientists and engineers, and so the ability to contribute something like this to a mission as exciting as OSIRIS REx really means a lot to the agency and to Canada. If you ask anyone that's ever built a flight instrument for space, they'll tell you all kinds of fun stories about the challenges they've had doing it. When you're building an instrument, you have an original design, you build a prototype, and you test it. What you want to do is something called test as you fly. Flying an instrument in space is a horrible place. So with flight instruments, what you need to do is put them on a table and shake them really hard to make sure that they're going to be able to survive the launch. You need to bombard them with radiation to make sure your electronics are still going to work. you need to put them in a chamber and completely evacuate it to make sure that everything still works when you're in a vacuum. In the end, ultimately what you have is an extremely robust system that you're confident that when you strap it to the side of the spacecraft, launch it, and fire it in space, it's going to work beautifully. I am incredibly excited to actually see what this asteroid looks like. When we get there and we see the first images and generate that first shape model, I think it's going to surprise everyone.
OSIRIS REx is a mission to get a sample from the asteroid Bennu, which is a carbonaceous asteroid.
We're going to image the asteroid as we approach it and as we orbit it. And then so OCAMS is really the OSIRIS REx camera suite. So we do a significant amount of imaging required for the mission.
OSIRIS REx is, of course, centered here at the U of A.
At the Drake building, which has been responsible for multiple space missions, many Mars missions, in fact.
Where we have all the facilities we need. We have a thermal vacuum chamber to do any TVAC testing that we're required to do. And then we have a Class 7 clean room where we build all the cameras and test them in the same environment.
The U of A has the Principal Investigator's Office with Dante Loretta, where he runs the science team and the entirety of the mission. We have the Spock Center, which does all of the processing of the spacecraft data. But then we have OCAMS, and OCAMS is the mission critical camera system.
The three cameras have very different roles to perform on this part of the mission, but they're the major visible light cameras for the spacecraft. We do have in the back of our mind that, most of what people are going to see from this mission is going to be the pictures of the asteroid. We realize we're kind of the PR firm for the mission besides all the science value that the cameras do.
It's one of the more complex camera systems because of the number of boxes, the number of cameras, the wide set of requirements that the cameras have to achieve, have to satisfy during their life.
The cameras just finished a milestone. They passed their pre-ship review, which is the final review that we have here at the University of Arizona before the cameras get delivered to Lockheed Martin, where they get integrated to the spacecraft.
For the flight units at the U of A, and a majority of the team, certainly the biggest part of our role on the team is over. It feels like it's not even running a marathon or an Ironman competition. I don't even know how to explain it. It's, I imagine if it was an athlete, it's like running up to an Olympics or something where you spend 3 or 4 years just working to this goal, and then you're finally there and you get to see how everything performs. It was actually fairly emotional. There's a lot of pride associated with all the work we did and getting it done, but it's also like, wow, this whole big chapter of our life is sort of coming to an end.
Always, these things are my babies, man. I've worked on them for, typically a flight camera, you bring it there, you've worked on it for a year.
The only analogy that seems to match is watching your kids grow up.
Delivering the flight instrument is, that's the pinnacle of this whole project, and getting it onto the spacecraft safe and sound is our primary focus right now.
You would think they're just cameras, the technology isn't even all that challenging, but everything is challenging when you do it in space, and it involves a lot of people, a lot of really amazing people with a lot of unique expertise.
I was describing to someone in the high bay the other day that these things end up looking like pieces of art, even though the intention was not to create art. But the perfection of building the instrument, making sure that the form follows the function.
It's a really specialized and unique endeavor. that we humans do. We like to think of it as routine because we've been doing it for so long, more than 50 years, right? But it's by no means routine.
Yeah, at the end of the day, it's a lot of pride that, say, hey, I was part of a team that did this. And, there's pride of being in the team. And then there's definitely, it's like, yeah, I was able to create that.
You were in the eyes of the explorer, and that's what these cameras are. There's our eyes out there exploring the universe, and you saw it for the first time. That's something nobody's ever seen before.
That to me is the exciting part, is when you get knocked backward in surprise and something completely defeats your preconceptions.
You'll absolutely never forget that. It is so unique, and not too many people get to see that.
After 3 months of science observations of Bennu, the science team will pick a location from where the spacecraft's arm will take a sample from the surface. The touch-and-go sample acquisition mechanism, TAGSAM for short, is a graceful, simple sampler head with an articulated arm. Once the sampler head makes contact with the surface of Bennu, a burst of pure nitrogen gas will push surface soil into the sample chamber. Surface contact pads on the exterior of the sample chamber will also collect fine-grained material as the collector touches down on the asteroid. This method was chosen because it eliminates the risks associated with landing on the asteroid. There are 3 separate bottles of gas that allow up to 3 sampling attempts, and about 60 grams of surface material should be collected. The asteroid is believed to be rich in carbon, a main element necessary for life. Organic molecules have been found in other meteorites and comet samples, showing that some of life's chemicals can be created in space. So scientists want to see if they are also present on Bennu. The OSIRIS sample return capsule is a Near Earth shell design. This design was also used on NASA's Stardust spacecraft, which successfully returned material from comet Wild 2 in 2006. In 2023, OSIRIS will return the sample capsule to Earth on the 24th of September, which will land at the Utah Test and Training Range in America. Once landed, crews will recover and transport the capsule to a staging area where it is prepared and transported to the Johnson Space Center Exposed Hardware Unit. Within a week of landing, the sample canister will be opened in a special clean room. OSIRIS REx is not the first space probe to visit an asteroid. Several have been visited over the past 27 years, notably the asteroid Gaspra, whose orbit lies very close to the inner edge of the asteroid belt. Gaspra was the first asteroid ever to be closely approached when it was visited by NASA's Galileo spacecraft, which flew by on its way to Jupiter in October 1991. Galileo then went on to visit the asteroid Ida on the 28th of August 1993. It was the second asteroid visited by the spacecraft and the first found to have a natural satellite of its own. Matilda was visited by the Near Shoemaker spacecraft during June 1997 on its way to the asteroid Eros. During the flyby, the spacecraft photographed a whole hemisphere of the asteroid, revealing many large craters on its surface. The Near Shoemaker probe visited Eros twice. first with a 1998 flyby and then by orbiting it in the year 2000, when it photographed much of the surface. On February the 12th, 2001, at the end of its mission, it landed on the asteroid's surface using its steering jets. In the year 2000, Atakawa was selected as the target of Japan's Hayabusa mission. The probe arrived in the vicinity of Atakawa on the 12th of September 2005 and parked in an asteroid-Sun line position at 12 miles and later 4 miles from the asteroid. Atakawa's gravity was too weak to allow the spacecraft to go into orbit, so the craft adjusted its path around the Sun until it matched that of the asteroid. Hayabusa landed on the asteroid on the 20th of November for 30 minutes, but sadly it failed to operate a device designed to collect soil samples. On the 25th of November, a second landing and sampling sequence was attempted, which was more successful. The sample capsule was then returned to Earth and landed in Woomera in South Australia in June 2010. In November of that year, the Japan Aerospace Exploration Agency reported that dust collected by Hayabusa was indeed from the asteroid. And of course, the Near Earth Asteroid Tatuus has been visited. On December 12, 2012, Tatuus passed within 43 million miles of the Earth. On December 13th, the Chinese probe Chang'e 2, which was on a lunar mission, flew by Tatuus at a distance of 2 miles and sent back some nice photos. Tatuus will approach the Earth again on the 29th of December 2016 at a distance of 24 million miles, when it should be visible in small telescopes. And so, in a few days' time, the OSIRIS REx spacecraft will be sitting on the launch pad and the NASA science team will be hoping for a perfect liftoff. That is all we have time for this month. Thank you for watching. Please subscribe to us on YouTube and visit our website astronspace.com, where you can see all of our past shows. If you like these programs, please share it with your friends and members of your local astronomical society. When we come back next month, we will be looking at the constellations of Perseus and Andromeda in the autumn sky. Until then, good evening.